I'm very excited that all these students are involved in the Cosmic Mining Project. It is fantastic to get so many people involved doing real science on this data that I've wanted to spend some time analysing, but don't have enough eye power and brain power to look at. So it's great that we're all collaborating together. And I just want to talk to you now a bit more about what we're doing once you've gone through these spectra, made some nice columns and classifications, and have a feel for what's going on with these objects. There are two main ultimate end goals of the project. There are the case where we want to find weird and wonderful objects that have been observed with the Spitzer Space Telescope in terms of its spectra, that we don't know much about. They don't follow the typical patterns of the type of objects that we look for. They may be doing something unusual, like the example Kieran showed. And with that, that means there's some new and interesting physics going on, or there's some unusual science. If we don't understand what's being shown, that means we need to get more information on it. If we don't understand the physics, this is really at the forefront of science. So by finding these things that may be confusing, that may arise a lot of debate among everyone who's classifying different objects, these are some of the objects that I am really interested in. And without everyone involved and collaborating together, these objects may have been left aside by previous scientists who just don't have the knowledge to understand and interpret what's going on. And what's great about this is there's a new telescope that's about to be launched towards October this year, the James Webb Space Telescope, which I'm going to call Webb from now on, which is like Spitzer. It operates in the infrared, and it has spectrographs available to us, so we can have a better look and a closer look at these weird and wonderful objects. The other main science project generated by this project is that we get large samples of objects that are the same. So, for instance, if we find all the young stars in the early stages of formation, we can put all these objects together. And as the objects observed by Spitzer are closer to us, we know that this is a sample in the galaxy that looks similar. And then we can compare that large sample of objects to data that we'll get with Webb or other data taken with Spitzer in other galaxies. So for instance, I looked at a lot of young objects in a nearby galaxy to us called the Large Magellanic Cloud, which is what this whole project is based on. And we can compare the two large samples of young objects between the two galaxies. And actually, by having this large data, we can see if there's any trends that change as the universe evolves, and as the galaxies evolve. By looking at different galaxies, we can look at different properties. And that helps us actually see how the universe is changing around us. So that's the main goals of this. I'm trying to generate large samples of same types of objects reliably, so we can compare, and also look for these unusual things which we don't really understand, which we can have a closer look at. Right now, I think I want to focus more on looking at strange sources again with a new telescope. So Webb operates in the mid-infrared. It has imaging, so it can take photos, but it also has lots of spectrographic capabilities. And actually, that's what really excites me, is these spectra are much higher resolution than what Spitzer is. Spitzer, it was tiny in comparison. It was less than a meter size in mirror, while the mirror for James Webb is 6.5 meters across. So that's a huge difference in sensitivity and in how much information we can collect on different objects. And what I want to say is examples of type of objects I'm looking for in the weird and wonderful category. So this is your nice spreadsheet. I hope you can see my cursor. If not, it doesn't matter, but there's the spreadsheet there. And then I'm filtering based on these columns and yes, no answers to your question of what type of unusual things we may be seeing in the spectra. So for instance, one thing, before we had a look through it and talked about the 10 micron feature in emission absorption, which is an indication of having oxygen-rich dust. And when we debated a bit to see if there was a 13 0.7 absorption feature as well. If that was there, that would tell me the star has carbon-rich dust. Physically, in terms of science, it's really difficult for an object to have both those components. It's normally oxygen-rich or it's carbon-rich. There is a very, very small number of objects known that have both those chemistries. And we don't know much about those objects or how that actually occurs. So if an object has both, I am extremely interested, and I have that make that to my shortlist of objects that I would like to ask for observing time on Webb to get a closer look at. Another column I'm really interested in is looking at stars that are in the very early stages of formation. So these are really, really cold. They have gas ices surrounding them. So they have carbon monoxide ice, not just water ice. They have other ices because it is a really cold environment, a really dusty environment. And how these massive young stars are formed is still an unanswered science question. We have some ideas, but we need more detailed look at a closer look at these type of objects to know more about them and understand more about the underlying physics which is going on. And there's lots of these within, or I think there's lots of these in the spectra that we have taken with Spitzer. But finding a large enough sample to be confident and say this is the type of physics going on is something that I'm hoping this project will return. And then one of the other final things I'm looking for is objects that cannot be classified. So if you get to the end and it doesn't fall in a nice class of objects, I'm looking at objects that meet that criteria, that have a lot of infrared excess. There's lots of interesting things going on scientifically for me, but we don't really know what they are. The more unknown something is, and it's got quality data, the more I'm like, oh, that needs to be followed up with more data. So based on your yes, no, there's other criteria as well that I'm interested in, but that gives you an idea of how I'm using the spreadsheets that you're returning to me to actually filter and pick interesting samples of objects of which I'd like to do some science on and compare to similar samples in other galaxies or from different science missions, or by making it to my short list of targets I would like to observe with the James Webb Space Telescope. One of the great things about observing with Webb, especially in the mid-infrared, which Spectra are taken, is the spectroscopic instrument on Webb is not just a high-resolution spectrograph compared to Spitzer. It also takes an image of the object at the same time. So in this case, this is called integral field unit spectroscopy. And I think in this picture gives you a good idea. You have your X and Y, which is your image on the sky of what an object looks like. But it also, every single pixel within that image, it produces a spectra of that pixel, which is a really powerful tool, because then we can actually see how the atomic emission lines or the dust or the stellar component varies across the image. So we can see actually if dust is produced closer to a star, if it's further away. In that spectra that Kieran showed, I have a feeling it has a stellar component close to the core, and actually then there's a ring of dust, sort of a cavity, and then a ring of dust further away, maybe imagine it a bit like a donut. That's what I think is going on with that object, but I won't be able to prove it unless I had data taken with an integral field unit to get both the imaging and the spectra at different points around the object. So it's a very, very powerful tool to understand, help me understand the science behind each particular target. So I've just given some points here. This will let us, by observing with the mid-infrared instrument spectrograph, it will tell us where the dust are and where the molecules are distributed around the star or galaxy. And then from its location, we can actually help then determine some of the physical conditions. So its distance, we can work out the temperature gradient, we can work out the density, we can work out the mass of an object. It is extremely powerful. And based on the student returns so far, from the long list of objects that are classified, there's about 20 or so that is on my long list of potential targets for Webb that I would like to observe. That isn't meaning to say that Webb will observe these 20 targets. It means that I would like to follow them further to look for more information. And then from that, probably narrow it down to a shorter list of objects. But this is very exciting so far. This is 20 targets that are unusual, that we don't really understand the science behind what's going on. So this is groundbreaking discoveries. So what I want to do then, once I've made my shorter list of interesting objects, is I want to do a literature search. I want to look through scientific papers, or students maybe could eventually get to the stage of looking through scientific papers and databases to ask, what do we already know about this object? Has other data been taken? Has it been observed with the Hubble Space Telescope, for instance? Has it been observed with the ALMA telescope? These are the type of things we want to ask and collect all that data together. Then another clue we can get at to see if it's what type of object something is looking at its spectral energy distribution. This is a bit like a spectra, but at a lot coarser resolution. And this is data points taken at a few broader wavelength ranges, maybe from the optical to maybe the far infrared. So a larger, broader wavelength range. And how that, if you plot the brightness of that object, those points versus its wavelength, you can see if you have a longer idea to see how the black body in continuum emission is behaving. And that will give us a bit more of a clue about what type of object one of these more unusual sources, which are difficult to classify, is. Another way to do that is also to look for higher resolution spectra, or spectra taken at different wavelengths, which may provide this additional information. And then finally, I want to collate that all together. And by doing this, I can have a better idea about what these sources are, these tricky sources that we don't really know much about. To give you an example of this, there are two main wonderful database options available to astronomers. The main one is called Sinbad, for stellar type sources. And you can put in a star's coordinates in the search field, and what returns is back an image. It gives you some basic information, and then down here it tells you actually how many references, how many papers have been published on this object. And in this case, only 5 papers in the entire knowledge of scientific literature has covered this data. And in this instance, it's a possible planetary nebula, but we don't actually know what it is yet. So that means that is actually a very good target to follow up, because we don't know what type of object it is. This is an example then. I can then look at its spectral energy distribution. So Spitzer operates at 5 to 25 microns in this range, but there's also down here some optical data available. And as you can see here from its spectral energy distribution, a bit like the continuum drawing class, if you draw a line up, we can see the spectra is still, or the spectral energy distribution is still rising, which hints that this thing is young or a galaxy most of the time. And there's a few points which are nearby stars from older telescopes that contaminate this. So sometimes these can be a bit more tricky to interpret. And here's a zoom in of a cleaned up version of the spectral energy distribution of this object. And then finally, there's another archive, NED, which I can search for to see if it has a redshift. And this is more for extragalactic sources. And then Vizio. And then Vizio is very clever. It takes away every single database and table that's been published in the literature and collates it all if I put into a search radius, and it gives me all this information. It can be very overwhelming at first. Most of the information shown here is just photometry points shown in the spectral energy distribution. But this is how I find out more about the object. Sometimes people have done some detailed analysis. And depending on what is returned here, it means, does it stay on my short list of objects still that I'd like to observe or not? And then putting it all together, I want to plot my spectra of the object. Again, here it's got a rising continuum. It has a dip, actually, a very slight dip here at 10 microns. So I know there's a silicate absorption here. And then because I'm looking for my camel sort of shape hump, I look near 20 and go, oh, look, there's another dip here. So this has both got a 10 and 20 dust absorption features. It doesn't have much else going on, but so this is actually one of the targets that's on my shortlist, because it's very, very red, which means there's a lot of dust there. The dust is silicates, but there's no other clues, either in the literature or from the spectra, telling us what this object is. And so I was very excited. And this object was actually discovered in the launch event for the IRIS project. So some students were going around, they didn't know how to classify it on this chart. And I was like, oh, what is this? And I got very excited. And I'm still very excited about this object. And there's a few more that students have discovered since then. So I just wanted to end it there, unless you would like to know more about how we would put in a proposal or not on the James Webb Space Telescope. So either let me know if you want to know more about that, or we can leave it here. Thank you.